In mathematics, the p-adic number system for any prime number p extends the ordinary arithmetic of the rational numbers in a way different from the extension of the rational number system to the real and complex number systems. The extension is achieved by an alternative interpretation of the concept of closeness, or absolute value. In particular, p-adic numbers have the interesting property that they are said to be close when the difference is divisible by a high power of p. The higher the power, the closer they are. This property enables p-adic numbers to encode congruence information in a way that turns out to have powerful applications in number theory, including, for example, in the famous proof of Fermat's last theorem by Andrew Wiles. P-adic numbers were first described by Kurt Hensel in 1897, though, with hindsight, some of Kummer's earlier work can be interpreted as implicitly using p-adic numbers. The p-adic numbers were motivated primarily by an attempt to bring the ideas and techniques of power series methods into number theory. Their influence now extends far beyond this. For example, the field of p-adic analysis essentially provides an alternative form of calculus. More formally, for a given prime p, the field QP of p-adic numbers is a completion of the rational numbers. The field QP is also given the topology derived from a metric, which is itself derived from the p-adic order, an alternative valuation on the rational numbers. This metric space is complete in the sense that every Cauchy sequence converges to a point in QP. This is what allows the development of calculus on QP, and it is the interaction of this analytic and algebraic structure which gives the p-adic number systems their power and utility. The p in p-adic is a variable and may be replaced with a prime or another placeholder variable. The adic of p-adic comes from the ending found in words such as dyadic or triadic, and the p means a prime number. Introduction. This section is an informal introduction to p-adic numbers, using examples from the ring of 10 adic numbers. Although for p-adic numbers p should be a prime, base 10 was chosen to highlight the analogy with decimals. The decadic numbers are generally not used in mathematics. Since 10 is not prime, the decadics are not a field. More formal constructions and properties are given below. In the standard decimal representation, almost all real numbers do not have a terminating decimal representation. For example, 1/3 is represented as a non-terminating decimal as follows informally. Non-terminating decimals are easily understood, because it is clear that a real number can be approximated to any required degree of precision by a terminating decimal. If two decimal expansions differ only after the 10th decimal place, they are quite close to one another, and if they differ only after the 20th decimal place, they are even closer. 10-adic numbers use a similar non-terminating expansion, but with a different concept of closeness. Whereas two decimal expansions are close to one another if their difference is a large negative power of 10. Two 10-adic expansions are close if their difference is a large positive power of 10. Thus 3333 and 4333, which differ by 103, are close in the 10-adic world, and 33,333,333 and 43,333,333 are even closer, differing by 107. More precisely, a positive rational number r can be expressed as 10e p q, where p and q are positive integers and q is relatively prime to p into 10. For each r0 there exists the maximal e such that this representation is possible. Let the 10-adic absolute value of r be 0, 10e equals 0. Closeness in any number system is defined by a metric. Using the 10-adic metric, the distance between numbers x and y is given by x minus y, 10. An interesting consequence of the p-adic metric is that there is no longer a need for the negative sign. As an example, by examining the following sequence we can see how unsigned p-adics can get progressively closer and closer to the number -1. And taking this sequence to its limit, we can say that the p-adic expansion of -1 is in this notation. P-adic expansions can be extended indefinitely to the left, in contrast to decimal expansions, which can be extended indefinitely to the right. Note that this is not the only way to write p-adic numbers. For alternatives, see the notation section below. More formally, a p-adic number can be defined as where each of the I is a digit taken from the set 0, 1, 9, and the initial index n may be positive, negative, or 0, but must be finite. From this definition, it is clear that positive integers and positive rational numbers with terminating decimal expansions will have terminating p-adic expansions that are identical to their decimal expansions. Other numbers may have non-terminating p-adic expansions. It is possible to define addition, subtraction, and multiplication on p-adic numbers in a consistent way, so that the p-adic numbers form a commutative ring. We can create p-adic expansions for negative numbers as follows, and fractions which have non-terminating decimal expansions also have non-terminating p-adic expansions. For example, generalizing the last example, we can find a p-adic expansion with no digits to the right of the decimal point for any rational number p, q such that q is coprime to 10. Euler's theorem guarantees that if q is coprime to 10, then there is an n such that 10n-1 is a multiple of q. The other rational numbers can be expressed as p-adic numbers with some digits after the decimal point. As noted above, p-adic numbers have a major drawback. It is possible to find pairs of non-zero p-adic numbers whose product is 0. This means that p-adic numbers do not always have multiplicative inverses, i.e., valid reciprocals, which in turn implies that though p-adic numbers form a ring, they do not form a field, a deficiency that makes them much less useful as an analytical tool. Another way of saying this is that the ring of p-adic numbers is not an integral domain because they contain 0 divisors. The reason for this property turns out to be that 10 is a composite number which is not a power of a prime. This problem is simply avoided by using a prime number p as the base of the number system instead of 10, and indeed for this reason p in p-adic is usually taken to be prime. P-adic expansions. When dealing with natural numbers, if we take p to be a fixed prime number, then any positive integer can be written as a base p expansion in the form where the I are integers in 0, p-1. For example, the binary expansion of 35 is 125 plus 024 plus 023 plus 022 plus 121 plus 120, often written in the shorthand notation 1,112. The familiar approach to extending this description to the larger domain of the rationals is to use sums of the form. A definite meaning is given to these sums based on Cauchy sequences, using the absolute value as metric. Thus, for example, 1/3 can be expressed in base 5 as the limit of the sequence 0.131313131313. In this formulation, the integers are precisely those numbers for which I equals 0 for all I less than 0. With p-adic numbers, on the other hand, we choose to extend the base pu expansions in a different way. Unlike traditional integers, where the magnitude is determined by how far they are from 0, the size of p-adic numbers is determined by the p-adic absolute value, where high positive powers of p are relatively small compared to high negative powers of p. Consider infinite sums of the form, where k is some integer, and each coefficient can be called a p-adic digit. With this approach we obtain the p-adic expansions of the p-adic numbers. Those p-adic numbers for which I equals 0 for all I less than 0 are also called the p-adic integers. as opposed to real number expansions which extend to the right as sums of ever smaller, increasingly negative powers of the base p. P-adic numbers may expand to the left forever, a property that can often be true for the p-adic integers. For example, consider the p-adic expansion of 1/3 in base 5. It can be shown to be 13,131,325, i.e., the limit of the sequence 25, 325, 1325, 31,325, 131,325, 3,131,325, 13,131,325. Multiplying this infinite sum by 3 in base 5 gives 0.00000015. As there are no negative powers of 5 in this expansion of 1/3, we see that 1/3 satisfies the definition of being a p-adic integer in base 5, are often used to represent the integers modulo p, while it is possible to use the approach above to define p-adic numbers and explore their properties. Just as in the case of real numbers, other approaches are generally preferred. Hence we want to define a notion of infinite sum which makes these expressions meaningful, and this is most easily accomplished by the introduction of the p-adic metric. Two different but equivalent solutions to this problem are presented in the constructions section below. Notation. There are several different conventions for writing p-adic expansions. So far this article has used a notation for p-adic expansions in which powers of p increase from right to left. With this right-to-left notation, the 3-adic expansion of 1/5, for example, is written as when performing arithmetic in this notation. Digits are carried to the left. It is also possible to write p-adic expansions so that the powers of p increase from left to right, and digits are carried to the right. With this left-to-right notation, the 3-adic expansion of 1/5 is p-adic expansions may be written with other sets of digits instead of 0, 1, p-1. For example, the 3-adic expansion of 1/5 can be written using balanced ternary digits 1, 0, 1, as in fact any set of p integers which are in distinct residue classes modulo p may be used as p-adic digits. In number theory, Teichmuller representatives are sometimes used as digits. Constructions. Analytic approach. The real numbers can be defined as equivalence classes of Cauchy sequences of rational numbers. This allows us to, for example, write 1 as 1.000 equals 0.999. The definition of a Cauchy sequence relies on the metric chosen, though, so if we choose a different one, we can construct numbers other than the real numbers. The usual metric which yields the real numbers is called the Euclidean metric. For a given prime p, we define the p-adic absolute value in Q as follows. Unless the numerator or denominator of x in lowest terms contains p as a factor, n will be 0. Now define x, p equals p minus n. We also define 0, p equals 0. For example, with x equals 63 550ths equals 2 minus 1 32 5 minus 2 7 11 minus 1. This definition of x, p has the effect that high powers of p become small by the fundamental theorem of arithmetic. For a given non-zero rational number x, there is a unique finite set of distinct primes and a corresponding sequence of non-zero integers such that it then follows that for all, and for any other prime, the p-adic absolute value defines a metric dp on Q. By setting the field Qp of p-adic numbers can then be defined as the completion of the metric space. Its elements are equivalence classes of Cauchy sequences, where two sequences are called equivalent if their difference converges to 0. In this way, we obtain a complete metric space which is also a field and contains Q. It can be shown that in Qp, every element x may be written in a unique way as where k is some integer such that x0 and each I is in 0. p-1. This series converges to X with respect to the metric dp. With this absolute value, the field Qp is a local field. Ostrovsky's theorem states that each absolute value on Q is equivalent either to the Euclidean absolute value, the trivial absolute value, or to one of the p-adic absolute values for some prime p. Each absolute value leads to a different completion of Q. Algebraic approach. In the algebraic approach, we first define the ring of p-adic integers, and then construct the field of fractions of this ring to get the field of p-adic numbers. We start with the inverse limit of the rings Z, P and Z. A p-adic integer is then a sequence n1 such that n is in Z, P and Z, and if n_m, then n_m. Every natural number m defines such a sequence by n equals m mod Pn and can therefore be regarded as a p-adic integer. For example, in this case 35 as a 2-adic integer would be written as the sequence. The operators of the ring amount to pointwise addition and multiplication of such sequences. This is well defined because addition and multiplication commute with the mod operator. See modular arithmetic. Moreover, every sequence where the first element is not 0 has an inverse. In that case, for every n, n and p are co-prime, and so n and pn are relatively prime. Therefore, each n has an inverse mod pn, and the sequence of these inverses is the sort inversive. For example, consider the p-adic integer corresponding to the natural number 7. As a 2-adic number, it would be written. This object's inverse would be written as an ever-increasing sequence that begins. Naturally, this 2-adic integer has no corresponding natural number. Every such sequence can alternatively be written as a series. For instance, in the 3-adics, the sequence can be written as 2 plus 2 3 plus 0 32 plus 1 33 plus 0 34 plus. The partial sums of this latter series are the elements of the given sequence. The ring of p-adic integers has no zero divisors, so we can take the field of fractions to get the field Qp of p-adic numbers. Note that in this field of fractions, every non-integer p-adic number can be uniquely written as p minus nu with a natural number n and a unit in the p-adic integers u. This means that note that S minus 1a, where is a multiplicative subset of a commutative ring with unit, is an algebraic construction called the ring of fractions or localization of I. Properties. Cardinality Zp is the inverse limit of the finite rings Z, pkz, which is uncountable. In fact, has the cardinality of the continuum. Accordingly, the field Qp is uncountable. The endomorphism ring of the proof a p-group of rank n, denoted zinc, is the ring of n times n matrices over Zp. This is sometimes referred to as the Tate module. Topology. Define a topology on Zp by taking as a basis of open sets all sets of the form UA equals n plus lambda par lambda Zp, where a is a non-negative integer and n is an integer in 1 par. For example, in the dyadic integers, U1 is the set of odd numbers. UA is the set of all p-adic integers whose difference from n has p-adic absolute value less than p1 minus a. Then Zp is a compactification of Z, under the derived topology. The relative topology on Z is a subset of Zp is called the p-adic topology on Z. The topology of Zp is that of a Cantor set. For instance, we can make a continuous one-to-one mapping between the dyadic integers and the Cantor set expressed in base 3 by mapping in Z2 to NC, where, using a different mapping, in which the integers go to just part of the Cantor set, one can show that the topology of Qp is that of a Cantor set minus a point. In particular, Zp is compact while Qp is not, it is only locally compact. As metric spaces, both Zp and Qp are complete. Metric completions and algebraic closures. Qp contains Q and is a field of characteristic 0. This field cannot be turned into an ordered field. R has only a single proper algebraic extension, C. In other words, this quadratic extension is already algebraically closed. By contrast, the algebraic closure of QP, denoted QP, has infinite degree, i.e., QP has infinitely many inequivalent algebraic extensions. Also contrasting the case of real numbers, although there is a unique extension of the p-adic valuation to QP, the latter is not complete. Its completion is called CP or omega p. Here an end is reached, as a CP is algebraically closed. However, unlike C, this field is not locally compact. CP and C are isomorphic as fields, so we may regard CP as a C endowed with an exotic metric. It should be noted that the proof of existence of such a field isomorphism relies on the axiom of choice, and does not provide an explicit example of such an isomorphism. If K is a finite Galois extension of QP, the Galois group Gal is solvable. Thus, the Galois group Gal is presolvable. Multiplicative group of QP. QP contains the nth cyclotomic field if and only if n p-1. For instance, the nth cyclotomic field is a subfield of Q13 if and only if n equals 1, 2, 3, 4, 6, or 12. In particular, there is no multiplicative p-torsion in QP, if p greater than 2. Also, -1 is the only non-trivial torsion element in Q2. Given a natural number k, the index of the multiplicative group of the kth powers of the non-zero elements of QP and Q times p is finite. The number E, defined as the sum of reciprocals of factorials, is not a member of any p-adic field, but EPQP. For p equals 2, one must take at least the fourth power. Analysis on QP. The only real functions whose derivative is 0 are the constant functions. This is not true over QP. For instance, the function has 0 derivative everywhere but is not even locally constant at 0. If we let R be denoted Q infinity, then given any elements R infinity, R2, R3, R5, R7, where RPQP, it is possible to find a sequence in Q such that for all P, the limit of xn in QP is Rp. Rational arithmetic. Eric Henner and Nigel Horspool proposed in 1979 the use of a p-adic representation for rational numbers on computers called quote notation. The primary advantage of such a representation is that addition, subtraction, and multiplication can be done in a straightforward manner analogous to similar methods for binary integers, and division is even simpler, resembling multiplication. However, it has the disadvantage that representations can be much larger than simply storing the numerator and denominator in binary. For example, if 2n-1 is a Mersenne prime, its reciprocal will require 2n-1 bits to represent.